current trends in satellite space industry is small satellites called cube satellites. These satellites can be launched for less than $100,000, which is very significant for satellites. Usually they cost in the $1 million range. One of the drawbacks to these satellites being small is they don't have a lot of power to transmit a radio signal back down to Earth. Also, they're in low Earth orbit, so they orbit the Earth continuously, and you only have about a 15-minute span to do communication with these satellites. To communicate with these satellites successfully, you have to have high-gain antennas to receive the weak signal, and these high-gain antennas have to be rotated by an azimuth elevation antenna rotator system to track the satellite as it passes over. So one of the things I want to develop is a portable system that can be moved from location to location easily to track these satellites. Also a small and lightweight system so that you could use smaller motors to track this movement of the satellite. So to do that, we need a miniaturized antenna. So based on research, I found that using a cross dipole, you could achieve a circularly polarized antenna with the antenna geometry itself. This is significant because normally in order to achieve circular polarization, you have to have external phasing networks, which adds both weight and size to an antenna. Right here, you can see a two-element cross-parasitic array. This is the basis for my antenna design. From here, I wanted to miniaturize the antenna. So part of that is reducing the overall width of the driver and director, and also bringing the driver and director closer together in spacing. So as we bring the director and driver closer together in spacing, what happens is the radiation resistance at the antenna tends to drop. Antenna needs to have about 50 ohms radiation resistance normally to match with the common coaxial cable that you would see, for instance, in your home theater system. Otherwise, power will not be transferred efficiently. So to compensate for this drop in radiation resistance, the geometry can be modified with a triple folded design that boosts up the radiation resistance back to 50 ohms. So that enables the close spacing. So we still need to miniaturize the actual elements themselves. To do that, you could use a geometry size reduction technique known as top loading, which can be seen here. You basically add these bars to reduce the overall length. That adds capacitance to the antenna and allows it to be actually smaller than the actual electrical size should be. The final design of the antenna used the triple folding method along with a curved top loading to get the geometry into the smallest size possible. The final size came about to be 1/4 meter wide and 0.04 meters thick. So significant size reduction from the actual standard antenna that would be used for cube satellite communication. So in the end, we have really good matching, which is important for power transfer, and we have good gain. We got about 5 dB of gain with a axle ratio that's under 3 dB. And the gain and the axle ratio both align in the same bandwidth, which is very important. And we got clean radiation patterns in both the theta and phi poles. This is the simulated results, and we also actually took this out on an antenna rotator system and measured the actual radiation pattern of the antenna to compare with the simulated results. Doing so, you can see that there's a very clear match with the simulated and measured results. A little bit of deviation, but that can be expected from errors in construction. We can't get the wires perfectly straight, which we do in the simulation, so it'll affect things a little bit. But overall, there's a very good agreement between the simulation and measured results. So in summary, a circularly polarized parasitic array antenna for cube satellites was designed and developed, and it's significantly smaller than the normal antenna that would be used. So we can use lower cost motors to actually move it and track the satellite, and it's a very portable system being lightweight. Some future work would be to add multi-band capability to this antenna. A lot of the satellites do employ different bands for communication. So if I could manage to put multi-bands in one antenna, that would also be highly desirable. Another thing would be to actually increase the gain of the antenna. This particular antenna is with a 2-element design, so the next step would be to add what is called a director to the bottom of this to try to actually get a little bit more forward gain and performance out of the antenna system.